Hello everyone. Today I will be going to discuss our project about the synthesis of bisphosphonate acids, alcohols, and amines to control polymorph formation during calcium carbonation. I'll begin by discussing the concrete industry. So concrete is the most used man-made material in the world. In terms of any material consumption, it is second only to water. The industry alone produces 8% of the world's CO2 emissions. There are a few different types of calcium carbonate polymorphs. For example, there is baterite, which is hexagonal in form, there's aragonite, which is needle-like, and there is calcite, which is rhombohedral. Of these, calcite is the most thermodynamically stable. So if you look at the bottom left corner of the poster, you can see a few of the different calcium carbonate polymorphs. In this study, we will be looking at the ability of biomimetic materials to control this carbonation and precipitation process of the calcium carbonate in cementitious materials. We are trying to see if we can enhance both the stability and function of building material. There are a few different small amino acids which were shown to influence this carbonation process, and phosphates and phosphonates are of interest due to their ability to strongly bind to calcium. For these reasons, we synthesized a series of bisphosphonate molecules of different charges and hydrophilicities, and we did this by altering chain length and the distal functional groups, like carboxylic acid, OH, and NH2. So if you look at the left side of the page in the background, you can see a few of the small amino acids and the molecule that we're trying to synthesize of different forms. So here in the center of the poster is the scheme and how we synthesized one of the bisphosphonic acid molecules. This example in particular shows the 7-carbon length bisphosphonate synthesis. It begins with a bromodecanoic acid, which undergoes esterification to turn the alcohol group into the ester. Next, we do the bisphosphonate reaction, where we use tetraethyl bisphosphonate and the ester we created earlier and attaches right here. Next, we want to remove the ester and turn it into an alcohol, so we do an ester hydrolysis. Finally, we need to remove the protectant group here, and to do this, we use TMSD protection to get our final molecule. The steps for the varying side link chains are very similar, and here are the completed molecules on the bottom. So to see the result of our molecules, we looked at them using AFM. So AFM is atomic force microscopy. It is a time-dependent characterization tool, and it allows us to see the polymorphs that are formed. Amorphous calcium carbonate, ACC, is a desired polymorph compared to the crystalline species due to the crystalline structures suffering from anisotropic mechanical properties. So the more hydrophobic C11 bisphosphonates, as shown at the table here, showed more formation of baterite and ACC at 58.75% here in the blue, compared to the C3 and C7 bisphosphonates, which had less ACC and baterite formation and more calcite formation. So as for future work, here are a few things we plan to do. We want to do time-dependent characterization of kinetic products. We want to do in situ experiments. We want to synthesize the different derivatives of bisphosphonates to contain the OH and NH2 groups. We want to do the synthesis of beta aminophosphonate molecules, and we want to synthesize aminophosphonate polymers. Thank you.